A quadratic function is any equation of the form ax squared plus bx plus c. And here a is not equal to 0. If a were 0, this wouldn't be here, and it would just be a line. All that being said, I have a couple of different graphs of quadratic functions. Looking at this one over here, f of x is equal to x squared. This is probably the most basic quadratic function we could have. So in this case, we have that a is equal to 1, and b and c are both equal to 0. And the basic shape is this U-shaped graph. This one's opening upward, and that's because a is a positive number. There's a positive 1 here. But if a were negative, the graph would be upside down. I'd like to highlight an important point on this graph, and that's this spot right here. So I'm going to label that. This is the point 0, 0, and that is called the vertex. Because the graph is opening upward, this vertex is the lowest point on the graph. So if it was opening downward, the vertex would be the highest point. Now over here, I have another U-shaped graph that's governed by this equation. But one thing to point out is the way that this is expressed, it's not actually of the form ax squared plus bx plus c. Like I have this thing and it's factored and it's squared like this. So what is a, b, and c on this equation? To figure that out, we actually have to square out the x minus 3 and then add 1. So let's check that out. So g of x is equal to, that's x minus 3 squared, and then plus 1. If you square x minus 3, you get x squared. You get negative 3 squared, which is 9, but you get two middle terms. You get a negative 3x and a second negative 3x, which gives you a negative 6x. If we add that plus 1 at the very end, this gives us the equation x squared minus 6x plus 10. So even though this equation was not of this form, we could transform it so it is. What we have now is that a is equal to 1, b is equal to negative 6, and c is equal to 10. I still knew that it was a quadratic because we had an x to the first power in here, and if you square that, it's going to raise this 1 to the power of 2. There's definitely also a vertex on this graph. I see that it's like right there, so let me label that. Okay, so it looks like the vertex, this lowest point, is at 3, 1. Now, how could you figure that out without a graph? Just by looking at this equation. And the way you can reason that out is by using transformations. If you want to go from this function to this one, I see there's two changes in the graph. This minus 3 is affecting the x values, and this plus 1 is affecting the y values. Essentially, we're going to go 3 places to the right for the x's, and then we go up 1 place for the y's, and that's exactly why this vertex is located right here, because it's a transformation of 3 to the right, and then up 1. Just remembering that the negative is actually going to have the opposite effect. It's going to go to the right for the x values. So the point of looking at a quadratic in this form is just to indicate that while this is a quadratic, having it factored in this way is useful because it tells you where the graph moves if you understand transformations. So there's another form for a quadratic. It could be something of the form x minus a number I'll call h squared, and then plus a number k at the end. And potentially, if a is not equal to 1, it could be like 2, 3, or 4. And because of this, I'll just put a number a in front of the x minus h squared part. So this is a general form, but this form is nice because it can tell you where the vertex is located. For example 1, for this quadratic function, I'd like to find the vertex, something called the axis of symmetry, as well as a min or max value. You can actually answer all of these things just by looking at the equation itself, but I included a graph as a guide. To start with, where's the vertex on this quadratic equation? Well, I can see it. It looks like it's right here. That appears to be -1, +7. But we should be able to look at this equation and figure out where it's located as well. I think it's worth mentioning that this is not of the form ax squared plus bx plus c, but that's actually better. It's in this factored form where you can understand where the points are based off of transformations. Here's what I mean. First, I'm changing the x's by adding 1, This will have, if we're starting at 0, 0, the effect of going left 1. The second thing is, well, there's this negative 2. The negative flips the graph, and then the 2 stretches it. But for the vertex, so it goes left 1 spot. We then multiply the y value by negative 2, which doesn't change it because the y value is 0. And then we add 7, and we end up at negative 1, 7. So I'm going to write that down, that the vertex is at negative 1, 7. So really all I'm looking at in the equation is this number here and this number here. The x value will be the opposite in sign of the one that appears here, because we're going to go left instead of right. And then this will be a plus 7 because the y values act the way you'd expect. This will be a plus 7, so this is a plus 7. So this form is really nice. It tells you where the vertex is located. Now here's a new term, something called the axis of symmetry. The axis of symmetry is the vertical line that goes through the vertex. So I'm going to draw that on here. So this vertical line is called the axis of symmetry. Symmetry because it's the line that splits the graph in half as a mirror image. So like this side is the mirror image of this side. It has some symmetry. And the actual equation is going to be x is equal to negative 1. It's x is equal to, so we get a vertical line, and the x value is also at negative 1. So that's the vertex, the axis of symmetry. And then, okay, well, there's also a min or max value. So which is it? Since this number is negative, the graph is opening downward. That means there is a highest point or a maximum value on our graph. So that maximum value occurs right here. So I'll say there is a max value of 7. And this happens at, I'll say it occurs at x is equal to negative 1. In example 2, we're again going to look at a quadratic function, and I want to find the vertex, axis of symmetry, a min and max value, but also determine what the domain and range of this function is. Now I included a graph, and it's a good thing I did because, well, this thing is of the form ax squared plus bx plus c. But unfortunately, you can't tell how this thing moves left, right, up, or down because it's not factored. Now, it looks like the vertex is right here. That appears to be negative 4, positive 3. So I'm going to go ahead and label that. It looks like this is where the vertex is located. But is there a way to determine that just by looking at this equation? That is, if your equation is of the form ax squared plus bx plus c. And it turns out there is. If you want to find the x value for the vertex, it's located at negative b divided by 2a. So you can look at these numbers, determine a and b, plug them into this formula, and it will always tell you the x value for the location of the vertex. So let's try that out for this problem just to see if it matches up. So a is equal to 1, and b is equal to 8. So the vertex, it should equal negative 4. If I put it into the formula, it's negative b is 8, and I divide by 2 times a, which is 1. Okay, this works. It's negative 8 over 2, and that does, in fact, equal negative 4. If you want to find the corresponding y value, which I know is 3, you can take this number, you can put it into your function to solve for the corresponding y value. So let's just check that. So if I put negative 4 into the function, the number we get back should be the y value here, which is positive 3. Let's see. So this is negative 4 squared plus 8 times negative 4 plus 19. All right, so f of negative 4, that is 16 minus 32 plus 19. And that works. F of negative 4 is equal to 3. So once you know the vertex answering the rest of these questions are relatively simple. By that I mean the axis of symmetry. I'll draw it on here. It's the vertical line that goes through the vertex, and that is at x is equal to -4. So this is the axis of symmetry. This was our vertex. Oh, this time there's a minimum value. There is a minimum value of 3 at x is equal to -4. So that's determined pretty much by the vertex itself. Now, domain is all real numbers. You can plug any number you want in place of x. The graph goes forever in both directions. So here's the domain. But the range is not all real numbers. It starts at 3 and it goes up. So if we want the range, so I'll put that over here. The range is from 3 to infinity. And that's everything for this problem. The last thing for this lesson is to use the vertex and intercepts to sketch a graph of this parabola. So the way it's written, probably should have y by itself. So I'm going to write this as y is equal to x minus 2 squared, but then plus 3. And once it's written in this form, I know where the vertex is. The vertex is at +2, +3. So that is right here. Okay, this graph is also opening upward because there's a positive number in front of where the x squared term is. So it's got to look something like this. There are no x-intercepts. So let's put that as a little note here. So there's no x-intercepts. If this is the vertex and the graph opens upward, it'll never cross this axis. The only intercept that we could possibly have is something on the y-axis. So what is the y-intercept? What does that equal? To figure that out, we can take x is equal to 0, put that into this equation, and solve for the corresponding y value. So if we do that, that is 0 minus 2 squared plus 3. And if you squared, I'll write it out. That's -2 squared. So -2 squared is 4. And 4 plus 3 is 7. So that's right here. Now, I know there's an axis of symmetry. So if you go 2 in this direction, you're going up 1, 2, 3, 4. That means if you go 2 in this direction, you also go up 4. So I'm just going to add this point just for a little bit of a guide for me when I sketch this thing. But my parabola is the u-shaped function. Well, I missed that. Way off. Okay, it is the, like I was saying, the u-shaped function going through those points. And that's it for this lesson.